Mom, if you're watching this, thanks for making all those cookies. Okay, we have another inelastic collision problem. This time with Ralphie and his pet tortoise. What? So here's how the problem's gonna go. Ralphie's pet tortoise, we'll name it something like Frank, right? Franklin the turtle. It's stranded on a rock in the middle of the river, but we have a rope swing tied to a tree branch directly over the rock. Ralphie's plan is to swing from one riverbank to the other and pick up his tortoise on the way. Okay? So here's like a really bad drawing of this because, we know how I draw, right? So there's a riverbank and there's another riverbank, right? Ralphie's tortoise is right here. And Ralphie's gonna, swing from here. He's gonna go pick up the tortoise and then and get out. Okay? Don't ask me how his rope does that. I don't know. This is just the drawing. So here's what we know. We know Ralphie's mass is 40 kilos. And we know his turtle's mass is 3 kilos. We also know that the opposite bank is 1.2 meters above the tortoise. What we're trying to figure out here is how high does Ralphie need to start this swing in order to make it? And we can actually figure this out even if this is an inelastic collision so that kinetic energy is not conserved during the collision. So here's how we do it. First, let's kind of like walk through this problem, and then we're going to end up going backwards through it. But let's walk through it forwards. When Ralphie is up at this height here, he has some gravitational potential energy. He has up here some mgh, and we'll call this like H1, and over here, we'll call this H2. But this is the mass of Ralphie times gravity times the height 1 that he is above here, above his tortoise. And what's going to happen is when he swings down, all of his gravitational potential energy is going to be converted to a kinetic energy, which is going to be 1/2 times the mass of Ralphie times the velocity at this point before he gets the turtle. So we'll say not for no turtle squared. Okay? Once he interacts with the turtle, I don't know how he grabs it or bumps into it or whatever, but when he gets this turtle, we can now conserve momentum. What's going to happen is Ralphie is going to have some momentum here. It's going to be the mass of Ralphie multiplied by his V naught, which is no turtle, plus the momentum of the turtle, which was 0 because it's at rest. And this will equal their final momentum. And since they're together, Ralphie's holding his pet, their masses are going to be combined. So mass of Ralphie plus the mass of the turtle multiplied by some velocity after the collision. Okay, so I'm going to call this VT for velocity with the turtle. Okay, but they are still at the bottom right here. We now need to swing them out. Well, since they still have some velocity, we can now, because the collision's over, we can now conserve energy and get back up to the top. We know we're going to have a kinetic energy at the bottom, a 1/2 m, which is really going to be the mass of Ralphie plus the mass of the turtle, because they're together, multiplied by with the turtle velocity squared. And this is going to be conserved until they get to the top. And that's going to be an mgh for gravitational potential energy. That's going to be the mass of Ralphie plus the mass of his turtle times g times h2, which we actually know that number. So if we go ahead and look at this, we're trying to solve for the h all the way back here. And if we were to put in numbers for some things, well, before we do that, let's make some easy cancellations. We notice that here mgh and 1/2 mr squared, or 1/2 mr v naught squared, these mr's go away, which is nice. Over here, the mass of Ralphie plus the mass of the tortoise, those are on both sides, so they go away too. And if we look at this, we know g, we're solving for this, so that's fine. We know 1/2, but we don't know what the velocity without the turtle is. So we can't really use this equation yet. We need to find that. We know the mass of Ralphie. We know the mass of the turtle. I would like to learn what this is. So that's fine that it's here, but I don't know what this turtle velocity is after the collision. So how can I get that? Well, I can come over here to our energy. I know 1/2. I know g. I know h2. I am going to solve for the velocity after the collision with our turtle. I'm going to plug it in here so it's now checked off, and I can solve for the velocity without the turtle. I'm going to put it back up top, and then I'm going to solve for the height of the bank. So we kind of walked through the problem forward, but then we're going to solve for everything backwards. So let's do this. If we go over here and we analyze this equation, we're going to have 1/2 times vt squared, which is what we're looking for, equals g times h2. Plugging in numbers here, we see that vt is going to be the square root of 2 times g, which is 9.8, times h, which is 1.2. We actually saw this exact same equation in some prior problems. This is also something that pops up in fluids for AP Physics 2. And when we do this, we find that this velocity here with the turtle is about 4.85 meters per second. We're going to swing that over to here. Now, over here, when we run this, we're going to have the mass of Ralphie is 40. The V no turtle right here is what we're looking for. This is going to be 40 plus 3, so it's just going to be 43. And then this is going to be 4.85. To solve for the velocity without the turtle, we just divide each side by 40. Don't accidentally just cancel out the 40 and 40. Remember, that 40 plus 3 is really 43. So when we solve for this now, we can say that the velocity of Ralphie without his turtle, no turtle, is going to be equal to 5.21 meters per second. Notice how Ralphie was moving faster, and then when he grabbed the turtle, they slowed down due to that conservation of momentum. So we'll take this 5.21 meters per second, and we will throw it. Whoops, not there. Where am I? We'll throw it all the way back up here into this quantity, okay? And we need to make sure when we do this that we square it. So let's just rewrite this because everything's getting confusing. We're going to have the mass of Ralphie multiplied by the height we're looking for equals, and that's going to equal, oh, oops, we won't even need that. What am I doing? We don't need the mass of Ralphie. He went away. This is gravity times the height equals 1/2 times this V no turtle squared. So to solve for that H, we're just going to get H1 equaling 1/2 times 5.21 squared divided by gravity, which is 9.8. Or I guess if you wanted to write this, you could write this as 1/2 like that. Doesn't really matter. But when you crunch these numbers through, you will find that the height of this bank needs to be 1.38 meters tall, which means Ralphie needs to start from a height higher than the opposing bank in order to get there, due to the fact that we lose some energy due to this inelastic collision whenever we grab our turtle. And that kind of makes sense for a real life scenario. You couldn't just, try to swing out and, from one height, make it to the other height. That's like a perfect ideal world, which we don't live in. We've got to be a little bit higher to make that entire swing. So with that, that's our second inelastic collision practice problem here. I hope you enjoyed it. It's nothing too crazy. We kind of had the idea for these energy equations, boom, boom, and boom. Just a little bit of understanding where we're going to find our values and how to swing them back through. So this problem is finished, and that really finishes out this unit entirely on work and energy. Next unit, we'll be going into a little bit of rotation, which is all about spinning, which basically covers everything from the year start to finish once again. So if you haven't watched all of these videos up until now, don't go to the next one on rotation. Go back and make sure you see everything, because we're going to need everything to move forward from here. But until next time, adios and take it easy.